In this video, we will talk about problem D, birthday gift from Codeforces round 936. You need to partition an array into the maximum number of segments such that if you take the bitwise XOR of all the elements in a segment, then you combine the results from each segment using bitwise OR. The resulting number should be less than or equal to x. If the final number is less than or equal to x, then you can increment x by 1, and now you would need to solve for the case when LHS is strictly less than x. If this is the binary representation of a number x, then what do the numbers that are strictly less than x look like? If you look at the set bits in the number x, there are 5 of them, then all the strictly smaller numbers can be divided into 5 different classes. You can pick this set bit and decide to unset it over here. If you do so, then all the bits to the right, the value of these bits do not matter, because no matter what you set them to be, this number is now always strictly smaller than this number. Or you can decide to keep this prefix as is and unset this particular bit. If you do so, then the value of these lower order bits become insignificant. Or you can decide to keep this prefix and unset this bit. Or keep this prefix as is and unset this bit. Same for this. So once we have computed the binary representation of x after increment, of course, then we just need to solve the problem when the LHS lies in one of these 5 different classes. That is, if we can find out the maximum number of parts that we can split our array into, such that the resulting OR of the segment has this form or this form or this form, etc., and we take the max over all such classes, then we will get our answer. Since these red bits are insignificant, let us chop these off from all the numbers, from the number x as well as all the array elements. To do that, you can use the right shift operator. So this operator will trim the last b bits of the number. Then recall that there was originally a 1 at this position. So how do you set it to 0? Remember that this operation cleared out all the red bits from here. So this is the last remaining bit. And how do you turn off the last remaining bit? You can simply subtract 1. Now that we have cleared out the red bits from the array elements as well as the number on the right hand side, we need to figure out the maximum number of partitions that we can create on the left hand side, such that the bitwise OR of these partitions is equal to this compressed number that we created. To do that, we need to understand the concept of masks and submask. So far, you have only been visualizing these sequence of characters as the binary representation of some integer. But let me give you a different perspective of these representation. Suppose you have 10 different elements labeled A, B, C, D, and so on. And then you try to create a subset from these elements. And you say that if you pick that element in your subset, you color it green. Otherwise, you mark it as 0, indicating that you left the element from your subset. So this would mean that you picked A but did not pick B and C. while you did pick D and E. So this encoding, this represents the number of elements and exactly which elements you chose for your subset. And this is usually called as a bit mask or simply a mask. What happens when you try to create another subset from the elements that you decided to take in step 1? So for example, you can decide to take this element again in your subset, and you can decide to skip this element and this element. So this resulting number that is formed is known as a submask. Submask is nothing but a subset of a subset. And if it is indeed a subset of a subset, then that means that if you have an unset bit in a mask, this submask can never contain a set bit over here. So for example, this element can never be a submask of this mask. Why? Because in this subset the element C wasn't included. If it wasn't included here, then it can never appear in any of its submasks. These are the 4 important properties of submasks that will be helpful in this problem. You should pause the video and try to prove each one of them by yourself. If this is the mask, then the only requirement for another number to be its submask is that the unset bits in this number should never be converted to a set bit in the submask. That is the necessary and sufficient condition for a number to be its submask. So if you look at this property 1 over here, it says that if you take the bitwise OR of mask and submask, you will get back the original mask. Why is this true? Because if the original mask contained a green element, then on the right hand side you will still have a green element, right? Because you are taking a bitwise OR, so one will be preserved. But if the mask contained a 0 over here, then it is natural to assume that the submask will also contain a 0 over here, and therefore this bit will also be preserved. So all the bits in the mask would be preserved, and hence this formula is valid. And using this, you can figure out if one number is a submask of the other. Next, if you combine two submasks using the bitwise OR operator or the bitwise XOR operator, the resulting number would be a submask. I leave the proof of this up to you. Finally, another important result is that if a mask can be represented as bitwise OR of some integers, then it is compulsory that all of these elements are submasks as well. Why is this statement true? Because if one of them is not a submask, then it means that it contains an illegal red bit where only 0 was allowed. So if it does contain a 1 bit where only 0 was allowed, this entire OR of these numbers would also contain 1 at that position, and therefore we have a violation because that bit would not be set in the mask, but it would be set on the right hand side. So it is compulsory that all of these need to be the submask. But keep in mind that this formula is not true if you replace this bitwise OR with bitwise XOR. And why is that so? I leave that up to you. Let me know your thoughts in the comment section. Now, each element on the left hand side should be a submask of the mask that is present on the right hand side. But how do we maximize the number of partitions that we have? To do that, notice a simple property of submasks. That is, if you have a submask and you do a bitwise XOR with some random number and the resulting number is still a submask, then you can confidently say that this number was also a submask, because if this is the bitwise XOR operator, you can send this over here, and from property 3 from the previous slide, we know that combination of submasks is still a submask. Therefore, that means that if you have a segment and in the segment this prefix is a submask, then the suffix of that segment will also be a submask. So that would mean that you would have two submasks that are present in that prefix. So if there are two submasks that are present in the prefix, you can simply replace this XOR operator with the OR operator and nothing would change, right? Because this is still a submask, this is still a submask, and the condition is still satisfied. So that means that in an optimal solution, every segment will contain only a single submask. And that gives us our greedy strategy, that is, start from the beginning of the array, keep going right until you hit an element such that this prefix is a submask. Once it is a submask, call it as segment 1 and then start from scratch and keep going right. Get the second segment, call it segment 2 and then repeat this process. This is the code for this problem. As discussed in the first slide, we increment x by 1 so that we only have to deal with the strictly smaller cases. Then we iterate over all the bits and recall that this bit represent this position, the blue bit. And of course, this has to be set in the original bit so that we can unset it over here. Then we need to remove all these irrelevant red bits. How do we do that? We right shift it by bit on X as well as the array elements. Then we simply apply the greedy strategy that we derived earlier. That is, we start with 0 segments, prefix XOR of the segment is 0, and then we iterate over all the elements in the array. As soon as we encounter the element, we take the prefix XOR of that element, and as soon as that prefix XOR becomes a submask of this mask that we are looking for, then we say that we have found one segment, and since we need to take the bitwise OR of all the segment, we do that in this have variable and we reset the prefix XOR for that segment. Finally, if the last segment was also a submask of the mask and we have achieved our result that we set out to achieve, then we will say that we found one possible answer and we will take the best answer across all the bits. Of course, the time complexity would be 30 into n, which is order of n. Now, here's a tricky question for you. So this code will obviously work, but if you remove this condition over here, that is, if you remove this condition of checking whether we achieved our final goal or not, the code would still work. And my question is, why is that? Like, why is relaxing the condition not affecting the final answer? Let me know your answer in the comments section below. Some of the concepts discussed in this video might sound out of the blue to you. For example, how does one even think about submasks in this problem? But that is just because you do not have a lot of experience solving bitwise operation problems. I have added some practice problem that uses bitwise operation manipulations, etc. in this Codeforces, in the CF step Codeforces group. You can check them out, and if you need any help or any debugging help or hints, etc., you can ask me on Discord or the Codeforces blog. All the code and the slides that you saw in this video, they'll be present on cfstep.com, and I will also link them in the YouTube comments.